So one of the sampling questions, you're actually given an incorrect name. So 2,2-diisopropyl heptane. So the first thing you actually have to do here is actually draw it out with the way they have indicated. So the parent name here is heptane, meaning how many carbons? 7 carbons. So let's draw out something with 7 carbons. 3, 4, 5, 6, 7. We'll number those 1, 2, 3, 4, 5, 6, 7. And it says 2,2-diisopropyl. So one of the things I didn't cover as much this year was, we'll get to this eventually, this is an isopropyl group, right? 1, 2, 3, 1, 2, 3. An isopropyl group is kind of like V. That's what an isopropyl group is. It's just a common name for a propyl that's bonded a certain way. So they're saying 2,2-diisopropyl. So that means on carbon 2, there's 2 of these things hanging off, right? So this is an isopropyl. There's 2 of them. But if you look at this, the problem is going to be what? Why is this an incorrect name? What's the problem?
It's not the longest carbon chain.
It's not the longest carbon chain. So let's find the longest carbon chain. Take a second and find that. Okay, so now I'm going to number in blue what could be the longest carbon chain, or I'll just circle it. Right, and in blue, if I zoom in a little bit here. Now in blue, I'm numbering 1, 2, 3, 4, 5, 6, 7, 8. Right, so the longest parent chain is octane. So if you look at the question, it's a multiple choice. Only 2 of them have octane, so you should be able to easily eliminate the other 2. And then on the octane, you would say, right, so using the blue numbers now, not the red, don't be confused. If octanes are parent chain, octane. What are our substituents? We have, looks like we have a methyl, and an isopropyl. So we for sure have to have a dimethyl. Now you go back and look at the answers. There's only one that has dimethyl. So that has to be the right answer. So really it would be, the correct answer here would be, if we call this an isopropyl, so it would be 3 isopropyl, 2, 3 dimethyl octane.
Oh.
Yeah. So this is kind of the one they're trying to emphasize here, identifying the parent chain. Like the take-home message of this problem is make sure you identify the longest continuous chain. That's the key to this problem, really. They're trying to get at. So let's look at this nomenclature problem. So again, first thing we have to do is identify the parent chain. So what's the parent chain going to be? It's going to be cyclobutane. Good. So cyclobutane. And we have 2 substituents, right? We have an iodo and we have a chloro. And we want those to have the lowest numbers possible. Right? So the easiest way to make those have the lowest numbers possible is they're both going to be, right? We say this is 1, and then it doesn't matter which way we go from there. 1, 2, 3, 4. So they're both 1s. Now, how do we order iodo versus chloro? Which one goes first? C.
Yeah.
So it has to be 1 chloro, 1 iodo, cyclobutane.
There's 2 that have chloro and then iodo and then the cyclobutane.
So one of the answers they give you is chloroiodocyclobutane. If they don't give you the numbers, that's ambiguous. That's not a good. Well, you can't. I don't know. It's unambiguous. I don't know where the iodo and chloro are at. You have to have the numbers in that case. If they don't have the numbers, I don't know if it's. I don't know what carbon those are on. Right. So you have to have the numbers in this case.
The only one you assume is when it's in alcohol.
Alcohols you can assume is right because alcohols always take priority.
Okay.
Right. Alcohols always take priority. If nothing else has that power.
Oh, okay.
Yep, so alcohols always take priority. I mean, the other way to do this, right? Again, multiple choice questions. Don't look at the answers. Don't look at the answers. Do the problem, then look to see if your answer is there. If you had done that, you would have found your answer but not get done. So we have a chair structure here. And what they're asking here, the question says, for the substituted cyclohexane compound given below, Highlight the substituents by clicking on atoms that will sterically interact with the methyl group in a 1,3 diaxial interaction. So we're focusing on the methyl group here. And they're asking what's going to bump into it when that methyl group is axial. So what else is going to be axial with it on the same side, right? It's saying what's it going to run into in a 1,3 diaxial interaction. So there's a problem here. What's the first thing you should notice? What's this about this methyl group? There's a problem. We have to flip, right? We have to flip the ring, right? We got to do a ring flip. The methyl group right now is in what position? Equatorial. So it needs to be axial. So we need to do the ring flip, right? We need to pull up 4 to be the head of the chair and 1 from being the head of the chair to be the feet of the chair. So we need to do a ring flip. And then once this is axial, we want to look for what else is axial on the same side of the ring, up, right? So this is up. So it's equatorial up. Once we do the ring flip, it's going to be axial up. And then we're going to see what else is axial up as well, right? So they're actually asking you to do a ring flip on your piece of paper as you're working on it. So I'll do the ring flip quick. All right, so the first thing we do with the chair flip, 1 pulls down. That's now the feet. 4 pulls up. And if we're worried about just knowing how to draw in, right, every carbon has an equatorial and axial position, but sometimes it's hard to say, well, which one is 3? I don't know. What I always look towards is either the head of the chair, it always has axial up and equatorial down. So in this case, axial up is going to be that CH3, and equatorial down is an H. And then from there, going out, everything else is opposite, right? So if carbon 4 is the top of the chair and has axial up, that means carbon 5 has to have axial down. Carbon 3 has to have axial down, right? Go every other one. So let's look at this to figure this out. So on carbon 5, what was on carbon 5 originally? There was a fluorine. The fluorine was up, but now we've done a ring flip, so it's still up, but it's no longer going to be, what position was this? It was axial, now it's going to be equatorial, and it's going to lean to the right or the left and up. Right, so if we divide the ring in half, remember, right, because these tough equatorial ones, like 5 and 2, are pretty tough to see sometimes, right? We know that equatorial, it's harder to remember, do they go right or left? Divide the ring in half. On the left side of the ring, equatorials go to the left. So that'd be the fluorine. The chlorine is still down, and it's kind of behind everything here, right, on carbon 5. Carbon 3 had an OH that was equatorial, and was it up or down, that equatorial? Down. So now it's going to be down still, but it's going to be axial. So there that is. What about carbon 2? What was on carbon 2? A chlorine, it looks like.
So it'll be equatorial to the right.
It'd be equatorial down and to the right, exactly. Right, this way would be the chlorine. Carbon 1 had a bromine that was axial and up. So now it has a bromine that's up and equatorial. Carbon 6 has what? Where was carbon 6? Carbon 6 had a fluorine that was axial and down. So now it's going to be down and equatorial. All right, so that's the basics of a ring flip. You should be able to do that. Now the part about this question was like, well, okay, fantastic. What was this question again? Right, the question was, what groups are going to be up on the ring? When they say 1,3 diaxial interactions, they mean what else is axial on the same side of the ring as the CH3. So what is going to be axial on the same side of the ring? F is not axial. That's equatorial. Fluorine's equatorial.
Chlorine.
Chlorine?
Isn't that on 5?
Chlorine's on 5, but it's down.
Oh.
And it's axial. It's not on the same side, right? It's axial, but it's not on the same side. So what's axial and on the same side as CH3 that we sometimes forget to draw in? Hydrogens. On which carbons?
3.
Nope.
No.
Which carbons have things that are axial and up on this ring? So 6.
And
Axial and up, 6 and 2. And what are those things that are axial and up?
Hydrogen.
They're hydrogens,
So we need to find 6 and 2 on our original structure.
right? Go to 6 and 2 in your original structure and highlight these H's. They're the ones that are going to have the diaxial interactions. I kind of had to wonky put this out here so it wasn't on top of each other.
You said 6 and 2?
6 and 2, right? Because, so another way to think about it, if carbon 4 is axial up, carbon 3 and 5 are necessarily axial down. So another carbon away would also be axial up. So yeah, my numbering is completely arbitrary. I always like to number maybe the top, the head of the thing is 1. But if I was naming this has nothing to do with naming. This numbering I have here has nothing to do with naming, right? It's just me for ease of my own brain. I just like to make this number 1.
Would you go from the
If-
methyl group?
If we did have to name it, what would be the highest priority thing on the cyclohexane ring? Of course, that would be the alcohol would always have highest priority, right? So my numbering has nothing to do with nomenclature. This numbering is just because I like to make the top of the chair, the head of the chair, 1. It's just easier for me to see. And I'm consistent always, and then when I do my flips, the 1 goes down, so what was the head becomes the feet, and that's always 1. Just easy for me to see. Right? So the hard part about this question, the hardest part about this question then is, what the question asks you to do is to go back to this original structure and find these 2 H's. So where are these H's on the original structure? They're both up for sure, and if they're both axial here, they both must be what here? Equatorial, right? So those H's they need you to circle or highlight is that H, and H on 6, which of course is up and to the right. So those are the 2 H's. These 2 H's are these 2 H's here. So you have to go back to the original structure and see, oh, they were equatorial at that point before the ring flip.
Why wouldn't they instruct you to do a chair flip?
They instruct you to do a chair flip, but by saying it has to have a 1,3 diaxial interaction, they're
Okay,
implying that must be flipped.
okay,
Another layer that's not necessarily getting at the heart of the question.
okay,
But challenging,
yeah.
maybe more challenging than I would put on exam,
Okay.
but this is challenging you. It's good. So one of the questions is, so let's get back to this idea about these 1,3 diaxial interactions. So this idea is what explains why bigger, larger groups, right, large groups, large things, never want to be axial. The reason they don't want to be axial is because, right, things in equatorial positions are pointed away from the ring and kind of away from everything,
Okay.
right? So that's good. They want everything, like, things don't want to be bumping into each other. Just like eclipse interactions are bad, right? Things don't want to be bumping into each other. But if you look at this ring, you'll see when something's axial, right? Like something's axial here, we call these 1,3 diaxial interactions because 1, 2, 3 carbons away is another axial thing. And it's kind of like they're like staring at each other in the face. It's bad, right? So these diaxial interactions are when molecules are kind of bumping into each other. They're not right next door, but in the ring, right, something's axial, it's going to see the other things that are axial on the same side. So they don't want to do that. They'd rather be equatorial. So the larger the group, the more important it is that it's equatorial, right? So if you have a large group, you want to do the ring such that it will be equatorial. And sometimes what they'll say is, well, one chair conformation has it equatorial, and the other one, of course, would have it. Right? If I'm up in equatorial in one chair conformation, if you do a ring flip, I'm up and axial, right? So you should be able to draw 2 chair structures and look at them and be like, which one's the better one? The one that has the larger groups away. So in this case, right, you'd want to have, right, they use tert-butyl, which is another common name for this. You'd always want the larger group, right, equatorial, right? The butyl group, the 4-carbon piece, you'd rather have that be equatorial than the CH3, the methyl, right? The larger groups you want farther away. So more carbons means larger, right? The size of the like iodine is larger than bromine, right? You'd rather have the iodine, right, equatorial, for sure.